Okay, thank you. Okay, so today we're going to start something, I mean, it's of course the same thing, but I'm going to start talking about TASEP again. And this lecture and all or most of the next one is going to be about how one can get to a solution of TASEP that's written in such a way. So first of all, one needs to get some formulas for the transition probabilities of TASEP. And these formulas should be nice in some sense so that we can take a limit. So that's what I'm going to show you, where the ideas come from and how it can be done. So just to remind you, what we have done in these last 3 lectures was, first I gave you like a general overview, but then we saw what the limiting formulas look like. It takes a bit because one has to define this strange Brownian scattering operator with these heating probabilities in there. So somehow these heating probabilities have to play a role in what I'm going to show you in these lectures. And then we saw some properties of this KPZ fixed point process and this nice integrability and all that. So as I said, we're going to go back to TASEP. Now, before doing that, I want to make a very small comment, and it's completely independent of TASEP. It's just that somebody in the audience pointed out to me, and he was right, that I said something that was a bit misleading at the very first lecture, so I just wanted to correct it. I said that nothing, or essentially nothing, is known for the Eden model. That's of course not true. The Eden model is sort of first passage percolation, and there's a lot of work done on first passage percolation. There's bounds, a nice bounce on the variances. So the problem is that that's a very complicated problem, and what I meant was to say that if you want to show convergence to things like Tracy-Witten distributions, Airy processes, so the type of thing that I'm talking about, that's very far from being understood. But it's not true that there's no work done on these models. So there's very interesting work, and I guess it's a very long-term project of many people, some people here as well. Anyway, so yeah. Okay, so TASEP. So for now, and actually for the rest of the, or most of the rest of the lectures, I'm going to be thinking about the particle system, not the height function. As we saw, there's a one-to-one mapping essentially between the two. So I can just think about this. So we have TASEP. So remember, we have these particles, and they jump around. This is going to be x1, x2. I will always order them in this direction. So it's going to be decreasing order as the label increases. And we're going to, let's suppose we have n particles. So for now, a finite number of particles and nothing else. Okay, so what one would like to do is to try to, well, find formulas for the transition probabilities of such a thing. And this is actually something that I think was discussed at length last week by Tomohiro. So there's a formula. So this is by Schutz in '97. And what he did is he used something called the Bethe ansatz, which is a big part of what Tomohiro was talking about last week, to show the following thing. So let me, okay. I'm calling x1, x2, and up to xn the positions of the particles. And what the Bethe ansatz does is it gives you a way, like a general way to try to guess a solution for a system like this, if you want. This comes from physics. So one tries to make a certain guess and then check and do something to compute the right formulas. So what he got is the following remarkable formula. He got the following. So let me first say to get the following. So if we start with particles at y1, y2, all the way to yn. And the formula I'm going to write, I think, in a way at least, Tomohiro probably wrote, or at least part of it. Then one has the following. The probability that x, my process at time t, equals x, given that I started at y, this can be written as a determinant. Not a Fredholm determinant, just the determinant of a matrix. So here it is, the formula. So there's a certain function f, which depends on an integer parameter, on time, and on another variable. So I'm not going to start to write too many formulas, but I just want to show this one. Okay, this big N, really a little n. Okay. So what he found is that you can write this transition probability. It's really what's the probability that I am at a certain position. So x1 is at some position little x1, x2 at some position little x2, and so on, given that I know the initial conditions. Well, this is given as the determinant of a certain function evaluated at all the possible differences. So I make up this matrix made up of this function, evaluated all the possible differences between the x's. And there's also this I minus j appearing here. And I have to tell you who's f, where, and again, we won't really use the formula, but at least I want to write it once. It's given as a contour integral over some loop around 0 and 1. So you take any contour going around 0 and 1, dw, and then so you have the following. That's the formula. Okay, so if you have seen these things before, I'm adding a 2 to the x there just for convenience, but the rest is all the same. Okay, so I'm not going to prove this. Again, this is part of what Tomohiro was talking about last week. You can also see there's a complete proof. So one thing is to find the solution, and for that you use the Bethe ansatz, or that's what Schutz uses. But if I give you the solution, then you can check. How would you check? Well, you have to check that this formula satisfies the forward equations for this system. That is just it's a Markov process with finite, it's a particle system with finitely many particles. You can just write down the Kolmogorov forward equation, or the master equation if you want, and then try to see if this thing solves it, and it does. Okay? So that's in my notes. You can see that in my notes, the proof is 2 pages or something like that. It's not so hard, but it's using heavily this determinantal structure. Okay, so that's where things stood in 97. And, well, the formula is explicit. Now, think about what we want to do. We want to take a certain limit of the system to get to this KPZ fixed point. And actually, if one thinks about it, so, okay, I have not been very clear about this, but as I take the limit, so the limit that I have written down, I have always been talking about the height function. Now I'm talking about particles. And if you make, at some point I will write it down, but if you make the connection about what do you have to ask of these particles to take the limit of the height function, it's pretty clear that you have to take a limit as n goes to infinity in particular. So in the scaling, this n is going to be like, actually, it goes, this n ends up being like a half epsilon to the minus 3 halves t plus lower order terms. So it means that at least I have to be able to take n to infinity in a certain way and with everything else at the same time. Now, if you try to take n to infinity here, you are going to be in trouble. Just because this determinant is growing, if you want. Right? So I'm taking the determinant of a matrix. If this was fixed, if this was, I don't know, 200, but fixed, then I can try to see if I can take a limit of the thing inside. But if this is growing and the matrix is growing, it's just not very useful. Okay? So it's a very nice solution, but in a way it doesn't get us where we want. And the other thing is that this is the transition probabilities. And I'm really looking for I would like to know, because that's the sort of thing I'm going to have to take a limit for. I would like to know what's the probability that x is less than something. Okay? So what I'm trying to say is that this is not the type of formula we need, it's the starting point. But then one has to do some post-processing to get to something. Okay, so this is the formula. Before continuing, I want to make a comment, because I'll show very soon. One checks that that for k, I should be careful. If k is non-negative, and I let psi of k at x, I'm going to define a new function, and it's going to be f with index minus k. T is going to be fixed, so I'm not putting it into the notation of the psi. T is just the time, the t-step time at which I'm going to try to find formulas for. And if I do this, okay, I define this psi, then this equals something known. What it equals is e to the minus t, t to the x plus k, divided by, it's going to be at x plus k factorial, and then something that I'm going to call c sub k t of x plus k. And this guy here, this c, this is the Shalyah polynomial. So it's the Shalyah polynomial. Shalyah polynomials have a parameter t and evaluated at x plus k, degree k. So what's a Shalyah polynomial? It's a discrete orthogonal polynomial, and it's the family of orthogonal polynomials which are orthogonal with respect to this weight. Actually, that weight. So this is just the Poisson weight. So the Shalyah polynomials are the discrete orthogonal polynomials with respect to the Poisson weight. So what that means, in case you have not seen these things, I'll say very briefly, it means that if I compute sum over x, okay, x positive, can you see this color or, yes? Okay, well, not very much. So if you compute sum x positive of e to the minus t, t to the x over x factorial, c k t x times c l t x, then this equals 1 if k equals L, 0 otherwise, or maybe with a constant in front, time a sub k. Okay? Probably it's, I mean, one can normalize the polynomials in such a way that, that you get 1. I think these are not normalized. Anyway, so just keep that in mind. Okay? And the proof of this is just, I mean, no proof is needed, essentially. You go to your favorite book or you go to Wikipedia and you see that this is the contour integral formula for the Shalyah polynomial. It's just exactly what it should be. I mean, it can be proved, but it's not even a statement. It's just, in a way, it can be taken as the definition of the Shalyah polynomial. Okay, so let me make a brief. I don't know how to call it. It's a sort of, it's a parenthesis because it's not part of the main story, but in a way I think it explains a bit of this main story. And this brief parenthesis is about push block dynamics on something called Gelfand settling patterns. Oh, no, Gelfand settling. Settling patterns. Okay? So just bear with me with a moment because we're going to see what this has to do with the story. Okay, so what's a Gelfand settling pattern? A Gelfand settling pattern is a triangular array of the form, I'll be careful with the indices. So x, I, j, 1 less than I less than j less than n, with interlacing. So it's much easier interlacing. So it's much easier to draw a picture. So it is the following: is I have, let's say I take n equals 4. So I'm going to draw a triangle of dots, and they have to be interlaced. Something like this. And so what I'm trying to say here is that, well, you can take this interlacing could be strict or not, depends on the case. In this case, I'm going to have non-strict interlacing on this direction, and then this is going to have to be strict. Like that. So what it means, it really means that I have simply a pattern of numbers. This could be integer numbers, real numbers. For us, they're going to be integer. And I put them here. And then on the bottom, I'm supposed to put another row with 3, and they have to be interlaced with the ones on top, and so on. Okay, so that's a Gelfand settling pattern for me. Is that clear? Yeah, and so this is yeah. So let's say Gelfand settling patterns of size with n equals 4 would be something which looks like this. So a collection of points on a triangular array is going to be a Gelfand settling pattern if it satisfies this interlacing. That's all. So this is, if you want to think about what happens, probably many of you have seen this, but if you have eigenvalues of a matrix, and then you start taking eigenvalues of the minors of the matrix, they start being interlaced with the ones on top. If I take a minor, if I take a 4x4 matrix, and then I take a 3x3 matrix, the 3x3 minor, the eigenvalues of the 3x3 minor are interlaced with the ones of the 4x4. Okay? Okay, it's just a simple definition of, if you want, this is a combinatorial object. Okay, so here is, so I'm making a relatively long story a little bit short, but there's a paper of Alexei Borodin and Patrick Ferrari. This is 2008, where they discovered the following thing. So I'm throwing some things under the rug because this had some story behind it. So people had been studying, I'm going to tell you exactly what, or at least approximately what people had realized first. But they realized the following thing. So consider, so we're going to put dynamics on a Gelfand settling pattern. So think of this as a particle system, but instead of being a particle system with particles on on Z, now you have dynamics on the whole array. And the dynamics are going to be the following. So just to make things simple, consider the packed initial condition, which means that I put particles as close as possible, satisfying the interlacing. So the packed initial condition looks like this. I'm going to draw it for 4 again. Okay? Because remember that this inequality is not strict. So I can push them all to lie on the same column. So that's an admissible Gelfand settling pattern. And now, okay, I'm not going to write this because otherwise I'm going to be doing this forever, but one way to think about it is the following. So you start like this, and then you think that these particles have like a weight, and the particles on the bottom are heavier than the particles on the these ones. This one is heavier than those ones are heavier than those ones, and so on. And now you do something like TASEP. So what you do is that each one jumps to the right at rate 1. Every particle jumps to the right at rate 1, but this is supposed to be dynamics that keep the whole array in this space. So you have to keep the interlacing. So the natural way to do it, or at least one natural way to do it, is the following. So since I'm postulating that these particles are heavier, and that's just to keep the interlacing. So if this particle moves to the right, then it pushes everyone above to the right, just to keep the interlacing. Okay, so if this one jumps to the right, everybody else has to jump to the right. If this one jumps to the right, it doesn't push this one, because this one is heavier, but it pushes the ones above. Okay? And on the other hand, if this particle wants to jump to the right, it's blocked by this one, because this one is heavy, and it's sitting right next to it. If this one jumped on top, so forget about this one if you want, but if this one jumps here, it would not be correctly interlaced with that one, because this one has to be strictly less than that. So this one, so let's say heavy particles block and push the ones above. Okay? Is the dynamics clear? So this is running, the whole array is running at the same time, and every particle can attempt jumps, but their jumps can be either blocked by a heavy particle on the bottom, or if it's killing the interlacing, then it has to push everyone to the right. Okay, so this is what's known as push-block dynamics for Gelfand-Tsetlin patterns. Now, so I said consider packed initial condition, and of course I can do the same thing with a general initial condition. But now let's focus on what happens here. So think about that collection of particles. I claim, and this is pretty clear, I claim that that's a Markov process in itself. So that marginal is Markovian. And actually, if you think about it, what's going on? This particle is actually jumping to the right at rate 1 freely. It's not disturbed by anyone, right? Because, okay, there's nobody below. It just pushes these guys, but it doesn't matter. This particle, well, the block dynamics, what they say is that it's going to be blocked by this one. Otherwise, it does whatever it wants. It doesn't see what's on the left. And if this particle is away, then it's going to jump until it gets blocked by this one. And so on, and so on, and so on. So the dynamics on these 4 particles is exactly TASEP. It's exactly what TASEP does, right? So I'm sort of building TASEP and putting something on top. That's one way to see it. And there's something that's, here comes the magic. So this is TASEP, and actually this is TASEP for any initial condition. So I can take any initial condition that I want, and I can run this thing, and it's going to be TASEP. But it turns out that for this initial condition, the guy on the top is also Markovian, and this is not obvious from the description that I just gave, but it's true. What the measure of this thing is, the law, is just the law of non-intersecting Poisson walks. So you just take a family of independent Poisson random walks, condition them on not to intersect, and that's exactly what this thing is doing. Okay, so this is non-intersecting Poisson walks. This is not obvious, not to me, to Patrick a little bit more maybe. And the way to prove it is actually to make the same construction in a different way. So here I sort of started from here and went up, and I said, okay, this is TASEP, and I get this non-intersecting Poisson walk here. There's another way to do the construction where you start here with non-intersecting Poisson walks, and you start building down, and then you check that what you get is TASEP. That's what they do in the paper. Okay, that's nice. Now, non-intersecting Poisson walks, if you look at them at fixed time, so for fixed, because remember, this is evolving in time. This is it's a particle system. But if at fixed time, this is given by something called the Shalyah ensemble. What's the Shalyah ensemble? It's essentially just a log gas with Shalyah weights, with Poisson weights. So I can forget about everything, I can fix T, and I can ask what's the marginal of this whole process, when I look at this row, just at a single T, and that's just the Shalyah ensemble. And this is a random matrix object, if you want. So you can look at the joint distribution of these particles are given by the usual product formula with a van der Monde determinant multiplied by the product of the Shalyah weights. It's like, say, the eigenvalues of the GUE, but instead of having Gaussian weights, I have these Poisson weights. So what's interesting here is that there's an intersection between the two. And on the one hand, you would expect, and it's true, that if I scale this Shalyah ensemble correctly, then the leftmost particle, which is like the leftmost eigenvalue, like the lower eigenvalue of a random matrix, but don't think about it like that, this is going to converge to the Tracy-Witham GUE distribution, and it's true, you can check. And this explains, just by this picture, why when I take TASEP with step initial condition, and I take the right limit, what I get is Tracy-Witham GUE. This is a way to see it. And it's a very nice explanation because it gives you a single object with natural dynamics where on one side, one projection is TASEP, another projection is a random matrix object, and you have exactly the right intersection where you want it, here, and then the limit of this looked at one way or looked at the other way, it's going to be the same, and there you see GUE. Okay? So I hope that's clear. I should also mention that that guy is also another particle system. It's called push TASEP, and one can do the whole thing, and actually one can prove that, just as we're going to prove that TASEP goes to the KPZ fixed point, one can prove that push TASEP goes to the KPZ fixed point. And if you want, it's for the same reason. Okay, this is all nice. The problem is that it doesn't work for general initial condition. This thing sort of breaks down. It says that if I look at particle number n, then as I take n to infinity, that's the same thing as scaling the Shalyah ensemble and looking at the first particle. And they're going to have the same distribution, of course, because they come from the same object, but for the Shalyah ensemble, I know that's going to go to GUE. That's what it's saying. So this is, I would claim that, at least to me, this is the simplest explanation of why Tracy-Witham GUE, like a real explanation. I can also do the proof. But this is sort of telling you where the thing comes from. And when I said in the first lecture, I think that it's pretty well understood how the Tracy-Witham GUE distribution comes in KPZ. The Tracy-Witham GOE, which is the one that shows up for flat initial data, that's not so clear. Okay, and I'm going to tell you now why, if you want, in this setting. Okay, so does that answer your question? Okay, so this works for packed initial condition, but if you want to, it means that I started TASEP with the step initial condition, because these are one next to the other. Now what happens if I try to do a general initial condition? So here's another way to think about this. This is, so now, maybe I should write this down. So now, if we fix t, so you can think of this as saying that the Tay-Sep measure at time t projects to another nice measure up in the Gulf unsettling pattern, which happens to be the Shalyah ensemble measure. Patrick taught me these things, a good way to explain this a couple of days ago, so I'm taking advantage of that. So think about it that way. You just forget about the dynamics, because you can fix t, and there's a measure, which is the whole measure on this triangular array, and you can think of the Tay-Sep measure projecting to a nice measure on the top, okay? So this says that the Tay-Sep law projects. So I'm going to do it like this, let's say. So the Tay-Sep law, which is the one on this side, projects to the top. I'm not sure if my grammar is correct, but let's not worry. So projects to the top as the Shalyah ensemble. And again, this is for step initial data. Okay, so as I said, this fails. So if you try to do this for another initial condition, it sort of breaks down. It's somehow, if you go through the proof, it doesn't quite work. But here's what Sasamoto found. So this is Sasamoto 05. And I should say that I'm mixing a little bit the timing of the story, because when Sasamoto was doing this, he wasn't thinking about these dynamics. He was thinking just about the measure at fixed time. And then later came this idea. But this is the picture one should have in mind. So you have this Tay-Sep measure, and it sort of projects up. What he found is that for general initial conditions, the Tay-Sep measure projects. Okay, it still projects to some other law, but it's a law. It's a sign measure. So if you change the initial condition, what you get here, when you try to do something like this, it's not a positive measure. It's a sign measure. Projects to a sign measure on the top of the array. That's what happens. So you can try it. You do it, you get something, and you get a nice, so essentially what I'm saying is you take the Tay-Sep measure at time t with some given initial condition, which is not step. You build a certain measure, so now time is fixed. You build a certain natural measure on these Gelfand-Tetlin patterns. And what you find is that as you do this in this natural way that I'm trying to emphasize, you get something, but the measure is signed. So there's no picture of an evolving, there's no possible picture of an evolving family of Gelfand-Tetlin patterns. There's just a measure, and the measure is signed. Okay, that looks very bad, because I completely lost this picture. But actually, it's almost not a problem at all. So I completely lose this picture and this nice connection with whatever's going on the top. But I still have a measure on a system of interlacing particles. And that's still a sort of, if you want, a random matrix theory object. I can still apply the same methods. And in particular, I can apply something called the Einard meta theorem in a certain version to try to say something about this measure. Okay? So again, the measure is signed, but the combinatorial tools, some combinatorial tools that have been developed in random matrix theory work exactly the same. There's just no problem. Okay, so that's the story. You get this sign measure on the top, you lose the picture, but you can still do something. Okay, but random matrix theory techniques still apply. That's the beauty of it. So now I'm going to make a huge leap. I'm going to tell you what Sasamoto, and then there's two papers doing this that to different extents, if you want. It's this paper, and then there's a later paper. I'm going to tell you the authors, including Patrick, where the outcome of all this is written down. Okay, so that's what I'm going to write next. Yeah, so you think of the idea is that you sort of think of this as a system of non-intersecting lines somehow, and you apply. So you have a determinantal measure. This determinantal measure is not positive, but it's a determinantal measure, and you can apply something which could be called like the extended version of the Ayyer-Meta theorem to discover what's the correlation kernel of this sign measure. So using the Ayyer-Meta theorem, you find the correlation kernel, and then you sort of project, and you get what I'm going to write down. Okay? And so if you know what the Ayyer-Meta theorem is, you know that in this correlation kernel, you have to invert a certain matrix. And this inversion, in the end, one can do it in a certain way using just linear algebra, and it's going to lead to what I'm going to write down. Okay? Now there's a big leap from what I'm doing there. So first of all, there's a huge leap going from this to that remarkable realization by Sasamoto, and then it's a little bit less of a leap because this is sort of you use known techniques, but you have to do it and prove things to go from here to what I'm going to write. And if you want to see the proof, well, you can go to the original papers, but this is also explained nicely in the lecture notes that I mentioned by Matetsky and Quastel. So there's these lecture notes on the archive, and you can see there the proof of this with quite some detail. So they write a little bit of the background of how one gets to using these tools here. Okay, it's not in my notes, but it's in their notes. Okay, so this is the theorem. So as I said, this is Sasamoto 05, and then Borodin, Ferrari, Fraunhofer, and Sasamoto. I think it's 07, maybe 08. And it says the following, so start ASAP with particles at x0, 1, right, larger than x0 of 2, and so on. So this is going to turn out to be important. There's a first particle, x0 of 1, and then to the left, okay, x0 of 2, and so on. So for what I'm going to write, I don't allow, because TASEP could start with a doubly infinite system. This is only for a finite system. Sorry, not for a finite, for what we call a right finite system, so a system with a first particle. So do that. Fix n in n, just some particle index. And I'm going to say it like this. So suppose you can solve the following bi-orthogonalization problem. Okay, and what this bi-orthogonalization problem asks you is the following. So find a family of functions phi k super n k equals 0 to n minus 1. So again, I fixed n I want to look at the distribution of particle number n. And to that end, I have to find n functions which satisfies the following. So number one, I'm going to ask that 2 to the minus x phi k n of x. And if you have seen these things, this 2 to the minus x is just because I put a 2 to the x over there. But that's just to make life easier later. So I ask that this is a polynomial of degree k, or you could ask that it's of degree less than n minus 1. So number one, these functions should be essentially polynomials. Polynomials multiplied by 2 to the x. And the key requirement is the following. I ask that if I compute the inner product, so I'm going to write it explicitly, the inner product in little L2 of z of, so I'm going to take my Shalyah functions, evaluated not at x, but I'm going to take the Shalyah function and I'm going to shift it by this initial condition. Okay? And I want to compute the inner product of this with phi n sub L of x. So this is just the inner product of the shifted Shalyah function. It's the Shalyah function that I wrote over there. It's not the Shalyah polynomials because it's sort of the Shalyah polynomials multiplied by the weight. And you have to shift the polynomial and the weight. So you take the whole thing, you shift it, you compute the inner product with phi. Well, what the Personalization problem asks you is that this thing should be 1 if and only if L equals k. So suppose you do that. I still haven't told you what's the theorem. So suppose you can solve it. Suppose you can find these phi's. Then, probably shouldn't have erased this, anyway. Then, the probability that x, t, n is larger than a equals the Fredholm determinant of I minus k n t, and I have to tell you who's k and t. I also have to tell you what's the Hilbert space here. The Hilbert space here is integers less than a, less than or equal to a, with k, t, n, x, let's say z1, z2 equals the sum from k equals 0 to n minus 1 of psi k z1 phi n, sorry. I have to put here the shifted Shalyah function times phi n k of z2. That's the answer. And if you were here last week, at least last Friday, which was the only day that I was here last week, well, I saw that Tomohiro was mentioning things like this. So he talked a little bit, or he mentioned briefly at least, these bi-orthogonal ensembles, and he did write formulas like this. So they live in the same world. Okay, and there's also, as I said, I'm always only writing things for the one-point distribution, but there's a similar multi-point distribution which you get by simply extending the kernel in a very similar way, okay? Let's say with an analogous extended kernel formula for multi-point. Okay, that's all very nice. And now, the nice thing about this, by the way, is that you have a Fredholm determinant. It's a Fredholm determinant on a space which is fixed. It does not depend on n. And you should think, the way to think about this, as I said, is that we're going to at least take n to infinity. We're going to scale many things, but in particular, we're going to take n to infinity. And, well, it means that I only, in quotes, but only, have to compute the limit of this kernel. So it's sort of in the realm of things that one can try to do. I have a function of two variables. I have to take n to infinity with some scaling in epsilon and all that. That's nice, but of course we need to find the phi's. So this is all, if you can solve this thing, then you have this nice formula. Which one? Here? Okay, this should, oh, that's true, thanks. So this is for, well, for that k actually. This is for k, thank you, equals 0 to n minus 1. Yeah. Because that's what I said. I mean, the k goes all the way up to n minus 1. N is fixed. I keep it in the notation because it's important to hide it, but it's completely fixed. And then I'm supposed to find n functions which do this. Actually, this is a linear algebra problem, if you think about it. It's really not more than that. It's just a linear algebra problem. It's a complicated linear algebra problem because you have to do it for all, I mean, you do it for fixed n, you find the phi's, but you have to do it for all n. And you should better do it in a way in which it makes sense, so that actually the dependence on n is sort of nice, so that then you can take a limit. Okay, so we need to solve for the phi n case. So let me give you the simplest possible example where this can be done. And you may guess already that it's step initial condition. Let's say example 1. Step initial data. So one should expect that this is going to be, okay, hopefully easy, but one should expect that this is going to be the easiest way because it's the easiest case because it's the one that's always easiest. And it's somehow, I mean, this one corresponds to this where we have this nice picture. So, okay, if this one is hard, then we're in trouble. But actually, it's very easy. So step initial condition can be written as this. So particle I sits at minus I, right? Because I have this packed initial condition where I put particles to the left of the origin. So let's write what this guy is. So psi k of, let's say, z minus x n minus k. This equals psi of k of z plus n minus k. Right? Because that's the initial condition. And now I write down what this is. I have this nice formula here, the one that I erased. But it told me that this is e to the minus t. Then I get t to the, so remember, so I have to put zn minus k, but there was a plus k. It was t to the x plus k. And you see what happens here. The k is going to go away. So this goes away. And on the bottom I have this, okay, I have 2 to the same thing, z plus n factorial. And then I should put here c sub k of t comma z plus n. So everywhere when I'm writing c plus n, I should be writing z plus n minus k plus k. Of course, that's just z plus n. So now, you look at this thing, and you say, okay, n is just, it's a shift, n is fixed. I'm just shifting, so I can sort of forget about it. Because I just shift, I mean, it's just a matter of shifting here the x. The 2 to the z is very simple. It's just sort of a conjugation, so I'll also forget about it. It doesn't make any difference, because if I want to get rid of that, I just multiply this by 2 to the opposite, so that would be multiplied by 2 to the z. And what I'm left is the Shalyah polynomial times the Shalyah weight. And what that means is that the phi's are just the Shalyah polynomials. That's what they should be, because they're exactly the polynomials that are going to do this. Just by definition. That's what a family of orthogonal polynomials is. Okay. Phi n k of x equals the Shalyah polynomial degree k of x plus n. So that's really as nice as one could imagine. And then what you get here essentially is, what you get here is sum from k equals 0. You can think of this as Shalyah polynomials times the right weight. So if, for instance, if you think about the Area kernel, it's very similar. In the Area kernel, I have integral from 0 to infinity, Area times Area. Here I have this integral from k to n minus 1, from 0 to n minus 1, of Shalyah times Shalyah. Okay, so this is sort of the usual structure in this sort of, in the nice versions of this. Okay, that's good. Step is very easy. So the half periodic case, which is what eventually leads to, I have to only do half periodic because I need to have a first particle. So here what you do is, I'm not going to do this one, by the way. So you put particle number I is at position minus 2i, meaning that I have particle hole, particle hole, particle hole, and so on. And then on the other side, I only have holes. And this one is harder, but doable by linear algebra. So you can just, I mean, again, this is a linear algebra problem, and if you fight with it, you get it. Actually, this is already contained in Tomohiro's paper, I guess, right? Yeah. And then it's done probably more rigorously in the paper of Bordin, Prahofer, Ferrari, Prahofer, and Sassamoto. Okay. So the question now is, what's the general case? And this is essentially where things stood for a while. Because if you want to take this limit and try to get this Markov process, then you need to be able to have general initial conditions. So if I want to use this idea, I need to find the phi's for general initial condition. So this is what had been done. There's also the stationary case that I mentioned, which is slightly different. It uses an extra ingredient, which I won't introduce. Okay. So I have 8 minutes left. Still have time to explain at least one of the things. So solution comes from two, okay, let's say from two ingredients. I somehow need to guess, because as I said, in general, you're not going to really solve the linear algebra problem. You could try, and maybe if I give you one special initial condition, not one of those two, maybe it's possible. But then what? You would have to do it for all the possibilities, so it's not really doable. So you need some other ingredients, something else that helps you see what you're supposed to do here. And there's two key ingredients. So the first one is a sort of reversibility for TASEP. I'm not saying that the process is reversible, but it's some sort of reversibility property, and what it says is the following. I'm going to explain it. So suppose I start with particles at x1, x2, up to xn, so that's my initial condition for n TASEP particles, and I ask for the probability that x at time t, particle number n, is to the right of A. Exactly the sort of thing that I'm writing here. So suppose you want to do that. Then, well, let me do a picture first, and then I write the answer. So the picture, I'll do it here. So the idea is the following. I have xn, x2, x1. So here is position A. And I want, so I'll draw some little circles here. We'll see why in a moment. Well, actually, I don't need them. So what I want this particle to end up at least at that position, or to the right. Okay? But now we're doing TASEP, and TASEP has this exclusion property. So if this particle lies to the right of A, then necessarily, another particle here, necessarily, I'll use, necessarily this particle has to have jumped and end up to the right of A plus 1. And this particle and that particle, every particle also has to jump, and they all have to lie to the right of the corresponding particle. So I can write that as follows. So this equals the probability with the same initial condition of xt n minus I lying to the right of, okay, let's see if I can get this straight, plus I minus 1, I guess. No. Yes, like that. For I equals 1 to n. So it is the same to ask that particle number n lies to the right of A as asking all the particles to the right to lie to the right of this configuration. Okay? That's clear. There's no other way for this to happen. But think about doing the following thing now. So TASEP, I can have particles jumping to the right, or to the right, yes. Or I could have particles jumping to the left, and the dynamics is the same, right? I could have particles jumping to the left with some exclusion rule, to the left. So what I'm trying to say is that now I could look at what I get over here, and I could run the dynamics backwards in time and see what happens, okay? And if you do it carefully, but I hope from the picture that's clear, and there's another way to convince yourself, which I can explain later. This is the same as if I start with particles at positions A plus 1 through A plus n. So now I start with particles here, and I sort of run the reverse dynamics. So I run it backwards in time. And I ask each of these particles to lie to the left of the corresponding initial conditions in the original. Okay, so I'm going to write this as reversed. So it's the probability for the reversed dynamics that xt I is less than or equal to, because I now want to lie to the left of these things, x n plus I minus 1. I think that's the right, I think this is the right index to put here. You can check. Is that sort of intuitive? So if I want all these particles to lie to the right of this, that's the same as asking all these particles to go backwards and lie to the left of that. You just follow the trajectory, and the trajectory going one way has the same probability as the trajectory going the other way. And then there's some shifting to do. This is actually much easier to see from the height function. The reversibility for the height function is very clear. So if I start something with something like this, and I let it run, so then I get something like that, the probability of going from this to that configuration is the same as the probability of starting here and now doing the little steps up to get to this configuration. And if you translate that obvious reversibility into what it means for TASEP, you get this. Is it clear? Okay, why does this help me? I'm going to probably use a couple more minutes, just because I want to finish the idea. I don't think it's Perk's property, because that's for the stationary case, and then you would get something about the distribution of this. This is just run the dynamics backwards. It's actually a very simple. So think about this. So I start with this narrow wedge, let's say, and I run it down, and then we're going to see something like that. And the probability that I went from this to that is the same. Actually, if you want to know exactly what I'm saying, is that let's say I fix some profile here. The probability of starting TASEP with this, and then I run it down, the probability that my later height function lies below this, it's the same as starting here and having it lie above there. It's I'm not saying it's completely obvious. It's not something, I mean, it's something one has to prove. But it's almost obvious. Okay? Now, okay, I'm saying this is one of the ingredients. Why is this useful? So of course, I mean, I'm running the reverse dynamics, but now I can just flip the picture around. So I can say, okay, I'm starting with these particles here and running to the left, but I can just sort of flip it. And now I'm starting with particles. I'm starting with particles here at, let's say I shift everything. So now I have -1, -2, -3, and so on. So I flip, I shift, and I have these particles going to the right and asking them to be to the right of certain positions, right? Xn, I don't know, to x1 or something like that. But this one I know, I just solved it. This is just the step initial condition. Right? So what I just realized, of course you have to do the reversing, the shifting and all that, but that's not a big deal. So what I just realized is that if I want, this is the main point, is that if I want the TASEP 1 point distribution for general initial condition, I can get by computing the TASEP multi-point distribution for step initial condition. Which I know. So actually, if all I was interested in was a probability like this, with general initial condition, I'm always writing the 1 point, but making sure that to always say that there's a similar one for extended kernels, because otherwise I would fill the whole board with these formulas. If all I wanted was this, I'm done. Nothing else to do. Exactly. That's exactly my point. Exactly. So I'm going to repeat what Patrick is saying. So again, if this is all I wanted, then I'm done. But this is not all I want because I want the whole process. So I really need multi-point distributions. And I've been saying that you always get the multi-point distributions. This is not a proof, but sort of conceptually what one does is you take the single point kernel and you extend it. And somehow that always gives you the answer. And then, well, you'll have to check somehow. But I have a problem because this is the multi-point distribution for step initial condition. I know it. But this is already an extended formula, right? Because multi-point distribution is given by extended kernels. And I cannot extend an extended kernel. It's already extended. At least I don't know how to do it. Maybe it can be done, but it sort of doesn't make sense. It's also not what I'm trying to do. Remember, what I have in mind is that I want to find the phi's. I'm just trying to use this to get an idea of what the phi's could be. But this first ingredient, what it tells me is that somehow the information that I need is going to be contained in the solution for the multi-point distribution with the simplest possible initial condition step. Okay, so tomorrow I'm going to start by, well, I'll probably have to write this down in the board again, but I'm going to start by explaining, essentially what I'm going to explain is that even though this thing is usually written as a formula for an extended kernel, there's an alternative formula which is not extended. It's not like, so I'll use that formula. It's not that I can take that formula and then extend. That's not a proof, and it doesn't work. Actually, it could work, but it's not a proof. But when we see what goes inside this new formula, it's going to be clear what we have to do. And we'll see that that formula, which is what we call a path integral formula, it contains inside a heating problem for a random walk. Exactly what shows up in the limit, and of course it's not a coincidence. So somehow we're going to be able to write this formula, the one that I need, in the form which looks a bit like a discrete version of these limiting kernels that I showed you. And from then, That's just sort of, you write it down, you see what it is, and then you try to start to guess. So from there, well, we won't do the guessing, I'll tell you the answer. So I will tell you who these phi's are, just by guessing if you want, but then you check. Once you know who they are, you just check they're a polynomial, you just check this, and this proof is actually easy. And then we have the phi's, and then we'll continue to try to show you how you get the limit. Okay? So that's the plan for the last lecture. That's it for today.